Problem statement. My project focused on cancer. Cancer is one of the top leading causes of death worldwide. According to data from the International Agency for Research on Cancer, in the year of 2020, there are 19.3 million people living with cancer. This number is projected to rise to 30.2 million in 2040, which means there will be a 55% increase within the next 20 years. Similar trend is seen also in cancer mortality. In 2020, nearly 10 million people died of cancer. This number is projected to rise to 16.3 million in 2040. It's clear that cancer still remains a progressive disease with a poor survival rate, and the treatment process is often long and costly. One of the emerging and promising approaches to increase cancer survival rate is called precision medicine in oncology, which is also called personalized medicine. This approach aims to incorporate multiple types of data, including the traditional histological and immunohistochemical imaging data, as well as the modern genomics and single-cell technology data. By incorporating multiple types of data and applying modern data analytics to it, this approach indeed has a hope to generate a precise cancer prognosis model that will help to improve patient outcome. But first, let's look at the data. Where does the data come from? There are several sources. First is research articles, second, clinical trials, and third, data in the 1,000 hospitals around the country. And the data types include 4 categories. First, the traditional imaging data, including both histological and biomarker immunostaining and DNA staining. The second category is the multi-omics data, including the genomics, proteomics, and others. The third category is the text documents, which include the standard operation procedure that was used to collect those images and omics data. This is important for correct data interpretation. The fourth category are the clinical records that contain patient information and the clinical outcome. The volume of this data is huge. Just to give an example, in the year of 2022, there are 340 new cases of breast cancer. And for each case, it's recommended to take 4 to 5 biopsy specimens. These amount to more than 1.2 million new breast cancer specimens in that year only. And this plus the archival specimens that have been accumulated over the decades, as well as specimens from other cancer types, which means there are millions and millions of samples there. And each of these samples is a gold mine of cancer molecular data. And here shows what kind of data we're looking at. Here are the traditional image data. You see the histological image, which shows the cellular and tissue structure. And biomarker staining, in this case, it's a HER2 biomarker for breast cancer. And also the DNA staining is in situ hybridization. In addition, you have these more newer data, including protein expression profiles, as well as genomic data. As you can see, the variety of data types and the variety of data sources make it impossible to have a fixed data structure for this type of data. Therefore, I propose a non-SQL database. There are several options of non-SQL databases, and I choose a cloud-based document database such as the MongoDB Atlas. In this database, each document will contain information about one cancer specimen. And collections are based on either on cancer type or the data provider. And this database will be managed by the NCI, a federal agency. The data providers and the data users will be given different access rights. Shown here is an example of a document. The MongoDB database accepts different types of documents, and this one is a JSON. In here, the data elements were saved as key value pairs. The first block shows the general information of this sample. Where does it come from? what's the ID, and the tumor type. Here it's the prostate cancer. And the Gleason score, which is the indicator of how advanced the cancer is. And the clinical outcome, the treatment strategies. The next block contains patient information that are relevant to the clinical outcome. No sensitive information is included. The third block, including the procedures that used for sample processing and the date of sample collection and the other information. The fourth block I show here, including the results. It could include images, like for the H&E staining and biomarker staining, as well as for the genomics data, which could be in text data file or CSV. The MongoDB database have a size limit of 16 megabytes for each document. Therefore, if you have a lot of images, it's better not to directly include the image in the document, but instead either use a URL or use MongoDB's API called GradeAF. MongoDB provides a query language that is expressive and simple and straightforward, very easy to learn. Here I'm going to show some examples of simple operations. In order to create a collection, all you need to do is just db create collection and add in the collection name. To add a document to a collection, just do db collection name, insert one or many to including one document or multiple documents into this collection. To find information in a collection, you use db collection name find. In this case, I'm trying to find the HER2 results and the H&E results from cancer specimens that are collected from patients that have been cured. You can also update the document by using db collection update. In this case, this patient's clinical outcome has been updated to remission. And also, you can delete one or multiple documents very easily. So why do I think this solution will be effective for my problem? There's several reasons. First, the MongoDB database is very direct and intuitive. Users can understand it without much explanation. Second, it's very flexible. It does not have a fixed schema. It's suitable for unstructured data. And different documents can even have in different fields. This is very suitable for the user case because data providers can have very different resources and capabilities in generating the data. For example, large hospitals may have genomics, proteomics, and many other data types. But smaller hospitals, the ones with limited resources, may only have the traditional imaging data there. And the document model preserve the relationship between the sample and the clinical outcome of that sample. Regarding CAP serum, MongoDB can always be consistent with the right client configuration and right options, and can always be available for reads as well. These are both very important for analysts to develop an accurate model for cancer prognosis. Lastly, MongoDB can also harness the power of Hadoop to generate sophisticated analytics and machine learning models and to support the operation process. In our case, it's cancer prognosis. Alternative approaches. Clearly, relational database does not work for my user case here because it's not designed to handle unstructured data, and my data are mostly unstructured. Graph databases is not needed for this project because the role of relationships between documents are not very prominent for this application. HBase also works well with unstructured data, and it's column-based database. It has more analytic capabilities at extreme large scale. But MongoDB wins at the documented data model because it makes it simple for developers, and also the multiple data types, as well as the more expressive query language. As Matt mentioned earlier, MongoDB can harness the power of Hadoop to generate more sophisticated analytics and machine learning models. Therefore, MongoDB is still remains the database of choice for my application. In summary, in this project, I have devised a database solution to support precision medicine in oncology, which is promising to generate a precise cancer prognosis model by incorporating multiple types of data and apply powerful analytics. My database of choice is the MongoDB Atlas database. This database allows the data providers to enter their various type of data, including images, multi-omics, documents, as it is. And once entered, these data are stored as documents. Each document contains the information of one cancer specimen, and the document are placed into collections based on cancer type or the hospital name. The use of a document data model as well as the expressive query language provided by MongoDB allow the user's data, which is an analyst, to easily understand the data and to perform queries quickly. My solution also included a combination of Hadoop with MongoDB database. By this, the analyst can harness the power of Hadoop to perform sophisticated analytics, such as deep learning algorithms on the huge amount of data in the database, and extract the features the most predictive of cancer progression, and based on these features to build a model that precisely predicts the cancer outcome. And this model can be supplied to the doctors to develop a personalized treatment plan and to improve patient care all over the country. The anticipated benefits of my solution are multifold. First, it's created a mutual beneficial relationship between data providers and analysts. The data providers, which the hospitals, have a huge amount of data, but they normally don't have the analytical power or capability. The analysts, on the other hand, don't have access to these samples or the data. So by bringing them together, they can complement each other in their capability and to help improve cancer care together. The second benefits is that it bridges the gap between large resource-rich hospitals and small hospitals, which is very limited resources. In that the small hospital now can gain from the insights that were derived from the data from the big hospitals and can use the insights to improve their patient care. Therefore, patients everywhere can benefit from this data solution.